Okay, I mean each of them we can go into details. I am going to give you slides, optional slides which you can read up because we simply cannot cover all of this. Overfitting, right, that is a big issue. I mean we have been seeing that all the time in your plots. Now the reason overfitting becomes even more of concern for neural networks is that they have this universal approximation property. Okay, what is the property? With a single hidden layer of a sufficient size, one can represent any smooth function to any desired accuracy. Okay, but you need a single hidden layer of an arbitrary size. Now this is a little dangerous because neural networks can overfit, like we saw polynomial kernels can overfit. So the greater the desired accuracy, the more hidden units are required. Okay, so then people have started looking at not only L1, L2 regularization, but there's something called dropout, where you can drop out, like at random you can mask and say set a weight to 0. Okay, so which means that the effect of some of the transmissions involving hidden layer units could be nullified. Again, it's a topic in itself, but regularization is one way we know we counter overfitting, and with neural networks there's a lot more regularization that you could do just other than just L1, L2. Okay. There's also early stopping. So if I had lots of hidden layer nodes, I could try and just stop early. I could also look at some validation data and how it's performing on that to guard myself against overfitting. Now what I'm going to do, I'm going to just focus on one of the challenging topics. How do I generalize? I want to avoid overfitting, but how about putting an intelligence into the network? Okay, so going back to my challenge, avoiding overfitting itself, let's now move on. So we are talking about avoiding overfitting or generalizing through smart network design. Okay, so I want to ascribe more semantics for a specific application such as say image classification or digit recognition, and in the process I might maybe address some other issues as well, maybe not these, some other challenges we see, for example computational time, and we will certainly see that we could reduce, number of parameters we could reduce. So these are all the keywords: parameter, tying, sharing, sparse representation. So there is a Lego world of neural networks, like you have played with Lego blocks, right? So this is will expose you to some Lego blocks. Okay, so I mentioned this again, it's a summary that you could have local optima, but say stochastic gradient descent, by avoiding even local minima often gives good generalization. Your quiz problem, today's quiz problem 3, we saw for a perfectly separable data set, we get norm W going to infinity. It's crazy, right? Now one way is to put a regularization, put a penalty on the W, but there are other things you can also do. So stochastic methods, for example, don't even try and optimize the original problem, don't even try and get to the global optimal or even a local optimal, but they therefore help you generalize. Okay, so as I said, that is a topic in itself, but it's a summary of how stochastic methods help. Now sometimes we need lot of training data. I mean, because you have a complex network, you will really need a lot of training data. One workaround is something called pre-training. What you do in pre-training is you try and reconstruct your original image, reconstruct your original data, because your data has come for free. What is expensive is annotations. If I just want to reconstruct digits, so imagine I had this network, but instead of my outputs being digits 1, 2, 3, 4, the classification, the class labels of the digits, suppose I were trying to reconstruct my original image itself. This is my original image. Now that image is coming for free, lots of such images will come for free. Now this can lead to good pre-training of a network. All you have to do is change the output layer. Okay, so again that can be dealt in detail, but this is just the intuition. and extensive computations and numerical precision. GPUs have of course come to rescue. So, but please don't demand GPUs for your projects. Architecture design, how many nodes, how many edges in each layer, and so on. So, dropout, for example, what it does, it randomly multiplies the output of a node with 0 using a random dropout bit vector. Okay, so basically you are trying to see, well, whether I should just drop out a node associated with its inputs. And finally, associating semantics by parameter tying or sharing and sparse representations. So what I am going to now delve into is one of them called a CNN, convolutional neural network. Okay, that's mentioned in that list there. There are many others, embeddings, inception, attention networks, and so on. The list keeps growing every second. Seriously, that's how this field is evolving. So I just want you to recap the concept of regularization. We know that to lower the bias in a model, including a neural network model, right, you could try and make the model simpler, right. For example, which of the two have higher bias, a linear classifier or a polynomial? The linear has higher bias, right. So if you want to lower your bias, what would you do? Increase the flexibility of the model. So when I say simpler, I meant just make it more flexible to learn. But the model therefore becomes a bit complex, becomes loaded, it has lots of parameters, it becomes heavy. Okay. So in addition in neural networks, you could also increase the number of epochs to reduce the bias, or you could also increase the network size to reduce the bias. As far as variance is concerned, what could you do? You could increase the training data set size. This is a general rule. That's why in the midsem also I said expected. I mean, at least you should appreciate that expected behavior of a model is that when you increase the training data set size, the variance reduces. Now you can always come up with some corner cases. For example, a stupid model which always outputs a 0, and unfortunately some of you just got caught up with that corner case, whereas the question was clearly expected behavior. Hope at least now you take this message that increasing the training data set size will lower the variance of a model. And then CNN, something like a smartly designed architecture, will also help you lower the variance. So we are just going to mark all these other additional properties. When you say avoid overfitting, we are also talking about lowering variance. We are also talking about lowering bias. With respect to a very over sophisticated complex network. There are also other methods of regularization, domain knowledge base like data augmentation and so on. I have given you other references as well. Okay, but now I really want to focus on intelligent design, and there is one last angle to this intelligent design. Recall from tutorial 3 we talked about the curse of dimensionality, right? That when we have n variables, then you can have 2 raised to 2 raised to n possible Boolean functions, which is too large. So as you can see, it's not just exponential, right? It's more than that. So this is one aspect of the curse of dimensionality. We also talked about VC dimension, and unfortunately or fortunately, neural networks have very high VC dimension. So how do you kind of control or tame a neural network in this high dimensional space and given its large VC dimension? So that's the other aspect of regularizing, right? So we are kind of taming neural networks. Intelligently. Okay, so that, what do you mean by intelligently? What are the aspects? Scalability, speed increase, stability of the model with respect to multiple random initializations. You will find that if I wanted to do just MNIST classification, rigid classification, without bringing in intelligence in the form of CNN, the models might not be very stable. You change the initialization, the model behaves very differently, and we saw that in some of our demos as well. And generalizable, yeah.
So can you please define objectively what does it mean to be intelligent?
So I'm going to give example for CNN, right? So that's the next topic. Okay. So now when we talk of CNN, I'm going to talk about these components. So depth or feature map, patches. This is a jargon we'll build on. Patches are filters, and some, unfortunately sometimes filters also called kernels. But I've avoided kernels as far as possible so that you don't get confused with your previous kernel friend. And then nonlinear activations, strides, padding, pooling. These are the different components, and we'll unfold them one by one. So depth is going to be very simple. Patches or filters are the key. Once you understand that, everything else probably will get clear. And stride is really a sub bullet under filters. Padding is also sub bullet. So this is a key point. And then there is another interesting dimension to filter where you can use them for pooling. I'm not going to get into other aspects of intelligent design such as inception. Then there's of course RNN, recurrent neural networks, and so on. Each of them will actually take up time. Okay, so I'm going to skip these optional slides just to give you an idea. This slide is interesting. How the introduction of something like CNN made a big difference. For so many years and decades, people have been working on something as simple as digit recognition, right? The accuracies and the speeds, I mean, they were they grew basically at a sluggish pace. And in comes AlexNet 2012. We suddenly find a big jump both in accuracy as well as in speed. Okay, and that's how much important this intelligent design has been. In addition, of course, to the availability of GPUs, but it's not necessarily only GPUs. It's a lot is attributed to this structure. Okay, so yeah, now let's start with a simple example, cat, right? So now what all do I want my model to be sensitive to while training to recognize cats? What do you see in this? I mean, you can further enlarge this data set yourself in your mind. What are the different components? So a cat, what do you see in these? Do you see a mirror image of the cat? What else do you see? Rotated, zoomed into one say the face of the cat. This is, and what do you see in the topmost right corner image? There's some background change. Okay, so we want to achieve as many of these, I mean the robustness goals as possible. I can now think of more examples. So by intelligent network, so what do you expect from an intelligent network? It'll train on this one image on the left while getting you implicitly all the training done on the other images. That's the most intelligent network you would expect, right? I don't need to keep augmenting all these other images in order to be able to build a robust classifier. So that's the question we begin with. So what do CNNs do? Now if you were to take this cat image here, question is what would these perceptrons, what would the activations correspond to? Not clear at all. So would the activations make sense is a question. And not only that, let's look at also parameter space. So let's say I wanted to identify scientists, there's one here, and if I had a 200 by 200 grayscale image with 40,000 hidden units, how many parameters you have? the product of the three, 200, 200 into 40k, 1.6 billion parameters. Okay, so as I said, that's also an issue we're going to deal with. It's also related to lowering bias. We don't want to deal with so many parameters, which will lead to overfitting, which will not give you scalability and so on. Okay, I saw a grayscale image. First thing I'm going to do is add this depth. This depth is nothing but color, to begin with. In the initial stages, think of this depth as color. And when we talk of color, we talk of RGB. Red, green and blue. Okay, so therefore what would happen? You would have a globe of 3. Okay, that's the first aspect. So this will be how many parameters? So earlier you had 1.6 billion and now it will be 4.8 billion parameters. And you can also compute the number of neurons. Now in this simple neural network, we are trying to be conservative in the number of neurons. We will have fewer neurons but no more number of parameters. So neurons is exactly how many? 1200 plus how many hidden layer nodes I said? 40k. Okay, so keep track of this. Now let's move to convolutional neural networks. What would they do? Here's a bird's eye view of what they would do. Now cat, I'm not very good at drawing cats, so I'll draw something simpler. A car. Okay. Now imagine all the cat transformations in the car. You could be zooming into the bonnet, you could be maybe the car met with an accident, right? Or it's like tilted. There are different kinds of tilts you could have in the car. And the car, of course, you want not just recognize my car but also other cars, right? So which means that you want to deal with different shapes here. There's a different proportions that are possible here. So what CNNs do is they first of all they say that, well, you need to identify small segments in this image. There's a wheel, there's a door. Okay, how do you do that? You consider locally connected segments. The second thing you do is the segment may be local, but the second segment can recur, right? So the wheel, for example, this is a locally connected segment. This is a locally connected segment, but wheels reappear. Okay, so that's the second component, that you could have weight sharing. Weight sharing to detect recurring components. So for example, the cat, the eye, right, the two eyes, now eyes recur. Now if for example, if you have person detection, it's even more, right? If you want 20 people in a scene, so there's the recurring phenomena is there in all cases. Now recurring could be as simple as edge. It need not be always a tire. It can be as simple as an edge. There are edges all over the place. Horizontal edges, vertical edges, right? Small curved curvatures. So any recurring component, you need the whole thing to be considered as one monolithic piece and share weights across all of them. So that's the second component. The third is equivariant representation. So let's say I shifted the car a bit in the image and did all my computations. Would you like my computations to be kind of robust to shifts of the image, right? So that's called equivariant, it's not invariant. So equivariant would mean that the neural network, the function applied after shift is the shift applied to the function in some sense, okay, very loosely speaking. This is equivariance. Can you think of anything else that is desired? Are these acceptable to you? Shifts in the image, path detection which may be recurrent, and local connectivity. Now these could be these could be part of the design of the network architecture. What else do you think could be of importance? What did we miss out from that nice set of images of cat? Rotation. So we have not dealt with rotation here. What else have we not dealt with? Background noise. Okay, so missing from here, rotation, background noise, even mirror imaging. Maybe to some extent you may get it, because we will get mirror images probably have the same connected parts. So we have not explicitly dealt with the mirror image here, and so on. Okay, so this is fully connected layer. What you see on the second is a locally connected layer, local connections, and the third is convolution. I don't know if you're able to see these colors. Do you see these colors? Yes. From behind? So you'll see that the edges, certain edges have same color, which means the weights are shared. So weight sharing to detect recurring components, and we'll come to equivariant soon. Okay. Now suppose we use these three, right? So now question is, with convolutional neural network from 1.6 into 3, which is 4.8 billion parameters, how much does it reduce? Okay. So do you reduce on the number of neurons? Do you reduce on the number of weights? Which is more important, reducing number of neurons or reducing on number of weights? As long as, so weights is more important as long as the neurons have some semantics. Okay, so as I said, we have already dealt with depth, which is RGB. Hereafter depth will just mean RGB and its variants. So there are different views, think of it as different views of the data, right? I said it's RGB as an example. But now these views, when I say this is views based on the neural network. Okay, so I will not be able to necessarily tell you whether it's a front view, top view, but as per the neural network. So you typically have these different channels. Like for red you have one channel, green you have one channel, blue you have one channel. Similarly, you can have multiple channels for these multiple views. Okay, so now we will move on to the second part, which is the patch. This is what we will do next, patch. And I am going to take this example in 1D to illustrate. Yeah. Which one? Depth. So views are just parallel channels. They're just parallel channels. Like you remember I began with this example of a scientist's face, right? And that was grayscale. And then I said, well, that grayscale could have had these, instead of grayscale, I could have had RGB. So R is one view of the scientist, G is one view of the scientist, B is one view. That's from the input side. But the network can say, well, you have 3 views, I'll create my own views. So you can have multiple parallel channels. So it's like, think of them as just different networks. On the hidden layers. Good point. So different views in the hidden layer through multiple parallel hidden layers. Okay, this is also part of depth. Let's look at patches. And I'm not taking an image, I'm just taking a sequence right now. We'll quickly generalize this to image. So I have x1, x2, x3, x4, x5, and what I want, as in the case of the car, so think of this as a slice of the car, right? But what I want is to first have locally connected segments to be captured. And the way I do that is by masking out anything that is not local, right? What you had earlier in the case of kind of generic neural network was that let's say Hj was a sum over all the i's of wij xi. That's what we had earlier. Now what will I do? I'll basically determine whether two should be connected or not, and that I do using a k. I mean, we call it a filter, but we'll denote it by k because the community also calls this a kernel. Okay, so I'm not going to call it a kernel, but we'll have to use k so that you don't get confused when you read the textbook. So the textbook often calls it kernel, okay, but it's not our RBF kernel. Okay, so now this k interestingly is a function of just one argument. It's just going to tell you whether two things should be connected or not. Think of it more simply as this delta ij. Think of it as delta ij, okay. Delta ij equals 1 if xi is connected to hj, and we find that for here x1 is not connected to h5. There's no h bit from x1 to h5. They're completely disconnected.
This would depend on the order of the input.
That's why structure is important, right? So image is not just a bunch of pixels, right? It's pixels ordered, and that's why we are now getting into intelligence. Intelligence is domain specificity. Okay, so I said through smart network design, but smart basically means domain specific. So CNNs were initially conceived of for images, though now they are also used for text. Okay, but let's focus on images. Okay, so if x1 is not connected to h5, then delta ij or delta 15 is 0. Now the way we do this, delta mi instead of hi, I've considered this case, xm going to hi, I've used ki minus m. Why? Because as exactly pointed out, there's a structure, there's a sequence. Why should I just keep it as delta ij or delta mi, right? I know that the distance between m and I is what will determine whether there's an edge or not. Okay, and the very specific semantics here is that kim is 1 if and only if m minus I absolute values less than equal to 1, right? Now please help me generalize this to 2D images. Images in 2D. This is, I want to be able to do this for cars. What would that expression look like? Quickly. Okay, so his point is indices on axis would change. There will be two indices. H will have two indices because again, now when I want to abstract away from the car and see whether there's a tire, H will be associated with two coordinates. The weights will also of course have those two specific indices. What will happen to K? K will have two arguments, but the two arguments are not like RBF kernels. The two arguments are two dimensions. Okay, so let's write that down. Hij equals summation over m, summation over n of xmn w mn comma ij, this whole thing into k I minus m comma j minus n. This is what you would have. Okay, and what's the intuition? Intuition is that neighboring pixels are more relevant than the ones further away, and also we will be more efficient. I think I have mentioned several things about this, right? Fast, speed in both training and inference. So I'll get, because of the local structure, I don't have to take all interactions, only sparse interactions. So this K is sparse with respect to the parameters. Now, what's the next step? So let's say we are done with locally connected segments. What's the second part? What did we want? The tire in different segments to be identified, right? So I just introduced you to this patches, filters, also called kernels. We are done with that. But now I'm going to talk about sharing within these patches. So these patches basically keep moving. That's related to the, actually it's related to the point of stride. The same patch is moving everywhere. It's not a different patch, right? There are two ways of looking at it. One is saying that parameters are shared. The other is saying, okay, there was a patch which computed something here. Now that same patch has moved somewhere else. Okay. So how would you write it down? So we have, I mean, how would the equation change? What would change in that equation? Would K change? Would W change? So I had HMN is summation, what is it, Hij is summation over M, summation over N of W Mn going to Ij XMN into K I minus N, I minus Mj minus N. Now what would change here? Would XMN change here? Input pixels are what they are. How would I achieve this? W0 prime being the same, W1 prime. Do you see that the indices have changed here in this figure? On the left, the indices are no longer W, Mn, Ij. What are they? So I replace this with exactly the same thing, right? So H5 when it's fed from X4, right? So I can use W I minus M J minus N. Okay, so the problem is I can't show 3D here. So okay, let me use color. So the X5 going to H4 is and X4 going to H5 are both shown here. Okay, so from what I know, H4 going to this is W1 and this is W minus 1. Okay, so I tried very hard, I couldn't get them on the same figure. I mean one of them is W1, the other is W minus 1. So depending on how you index. Thanks for pointing that out. On the left hand side I was shown for a 1D case, right? So if you want to be consistent with the left hand side, you can just do Wjn here. Okay. Anyways, I don't think that's important. We can 1-dimensional, 2-dimensional. Now you should be able to interoperate. Okay, so this is what it looks like for 1 dimension. Hi is xm into wi minus m, ki minus m. For 2D input, you'll have exactly these two components. And now the additional dimension is that neighboring signals affect in similar way irrespective of location, right? So the same thing is now being moved. Don't be over fixated on the fact that this is a left tire and this is a right tire. Both are tires. So learn to detect the tires in your hidden layer. And now we have an additional, we said many things, right? We wanted speed to improve, but now also storage has improved. Because you have fewer parameters. Okay, it reduces storage requirement while being very reasonable in terms of the domain itself. Okay, so now some few more things. So we have kind of moved to this thing called stride. But now within stride there's one more interesting thing. I mean, let's say I keep moving this structure, right? I'll have this patch, I'll move this patch. The same patch is moving, which means the parameters are shared. But does it have to move 1 pixel at a time? Can it move few pixels at a time? Because the segments are contiguous. So will it really matter if I kind of jump sample by say 5 pixels? Turns out that it doesn't hurt very badly as long as you sample or jump reasonably, right? So this is the third. Consider only HIs where I is a multiple of S, some S, okay. So intuition is stride of S corresponds to moving the patch by S steps at a time. And the idea here is image doesn't change very drastically, right? It changes very gradually. Then the question is what to do at the corners. I'll keep moving by small patches, but suddenly with the patch it comes here or here. I mean, I want all the gradient information, the rate of change, etc. even at the corners. I will overflow. What do I do? Pad. Okay, so padding is basically to deal with corners. Pad. So what are the pads possible, right? Let's say I have this image. So I'll say I'm going to expand this image slightly so that I can accommodate the overflow in the patch. So I could pad this with zeros everywhere, right? 0 means the pixel value is 0. Just so that I allow algorithmically that the patch can move. The other possibility is I just stop the pad, the patch here. I don't let it account for all these smaller kind of gradient and other information on the corners. So that gives you two strategies. Either you can have zeros at the edges. This is called same padding. There's not too much story behind why it's called same padding. Or have no padding at all. It's called valid padding. Again, no rocket science in the name here. So this is one more aspect of padding. Okay, and I'm going to give you the small exercise. Can you guess what each of these filters does? This filter. Okay, so which edge? Any edge? Okay, this is vertical edge. Okay, it's called the Sobel vertical edge detector. What about this one? Horizontal, that's easy. The remaining two, you have something called image blurring filter. I showed you the example of cat with background noise, right? So you may want to kind of take the average of all the neighboring pixels, especially when there's a little bit of noise on top of it. Or you can also have image sharpening filters. Okay, so image sharpening is typically used when the noise makes it difficult to understand the edges from the background. Blurring is used when there is too much contrast already in the image. Okay, so there's a nice blog here you can look at. And the idea is that we want to be able to learn the weights from the data. These are some example filters which you can spoon feed. So now let's quickly look at computation. Okay, so there are 4 cells. Let's say I have these 4 cells which are now and there is 0 padding. So 0 padding along the corners. Each dimension is 200 by 200. I have shown this think of this 3 as R, G and B. Okay, this is what I meant by the channel or the depth, feature map, etc. Okay. And now this patch is going to be moved. What's the size of the patch? 3 by 5 by, so basically 3 is as I said the depth part. 5 by 5 is what will be actually moving. 3 will just keep moving along. Okay, so now I move it. Now I have actually, this was in the edge where I had padding of size 4. Now I have moved it slightly inside by one cell, and now keep moving this until this corner. Okay, so I have kind of moved it this way until we have reached here. And the output, what is the size of the output here? What's the size of the output? 204. Now the 3 depth has become 1. I have shrunk it. You don't have to necessarily shrink it. You can retain the 3 if you want. But we are more interested in the x and y dimensions. The depth we are not very concerned right now. So what we have seen so far is sparse interactions, parameter sharing, and finally equivalent representations, which is before I do a shift, if I compute the function, I get the same effect as computing the function and then doing a shift. Okay, these 3 things we have seen so far: parameter sharing, sparse representation, and equivalent. F of g of x is g of f of x. Okay. Now we come to some computation. So this is where we began, right? The hidden the input image had size 200 by 3, 4.8 billion parameters. Now how many parameters does my CNN have, and how many output neurons will it produce? I mean, because we are now dealing with strides, patch, and so on, right? So we need to answer these 2 questions. So let's quickly look at this in a generic setting. So let's say I have m by m n image, right? So I have this m by n image, and the filter is of size p by q, and let's say so this is filter size, and let's say I do a padding, a 0 padding of size d on all sides. Now what will be the size of the output? We will just stop with this. What will be the size of the output? Yes? As I keep moving, how much can the p by q thing move? It can move up to d, right? It can move, which means it can move from d here to d there, both sides. So it's not just one way. There's a d here as well. So output will be what? So I also said that the q can jump, and how much can it jump? The patch can jump by a stride of small s. Okay. S is the stride length. So the patch can skip and move. So whatever you do, you'll have to divide somewhere by s. That much intuition should be clear. Okay, so what would it be? M plus 2d minus q divided by s plus 1 times n plus 2d minus p by s plus 1. Okay, this should be very easy to figure out. M plus 2d minus p by s plus 1, n plus 2d minus q by s plus 1. This is the dimension, and if you want to retain the same size, all you have to do is set d to be p minus 1 by 2 and s to be 1. You will get the same size as the output.